So in this lecture, now we are going to look at torsion of shafts or torsion of circular shafts. So when it comes to the torsion on circular shafts, you can look at this as an example. So if you have a shaft like this, and if it is tried to twist using a torque, then that is called torsion. And what happens when you apply a torque? The torque transmits from one end to other end. So when you apply a torque on one end, it will get transferred to the other end. So it transmits power from one point to another using rotation of shafts. So this happens in many industrial applications. So we are going to look at the stresses and force or torque and how to calculate them. A good example is a screwdriver. So when you tend to rotate from one end, the other end, the torque is transferred through this shaft to the other end, and where the screw is either get tightened or get loose. So this is a classical example of a torsion or torque, application of torque. So in a car you have this drive shafts which undergoes torsion, and a propeller shaft in a ship undergoes torsion because torque is applied on one end and transferred to the other end. And in a turbine you can see the effect in a turbine. So when you look at this, when you apply a torque, then there is a deformation is occurring in these elements, and if you look at this deformation, there are stresses, and we are going to define those stresses. So let us look at the shear deformations. So when you apply a torque, due to this rotation of the shaft, there is a distortion in the element, and that distortion is causing stress. So if you look at a shear stress and shear strain, so this is when you apply a torque, a shear stress, then it get deformed or distorted by an angle gamma. So this angle is called shear strain. So if you look at the stress strain behavior of shear stress and shear strain relationship, you will get a linear relationship like axial stress and strain, and then you will have a plastic region, and this is called yield shear stress. And then you have a shear modulus G, and the behavior is a linear elastic. So the stress is proportional to strain, and then you can substitute with the constant G, and that G is shear modulus. So this is the basic equation that relates stress and strain, shear stress and shear strain. Now if you look at torsion in a thin-walled circular cylinders, so thin-walled circular cylinders means we know the definition, R over T greater than 10. So in a thin-walled circular cylinders, when you rotate this by, when you apply a torque on one side, it rotates by angle theta, and then the angle reduces, and then the torque is transferred on the other side. Okay. So that is the effect due to the torque. Now let us see how we can relate this. Okay. So if you can relate this gamma can be defined as R over L into theta. So here it rotates by angle theta, and then that the angle is defined by r theta, the deformation is defined by r theta, and the gamma is r theta over L, because that is the strain. Now if you look at the cross section, so this is the basic equation, tau is equal to G into gamma, so that is G is shear modulus. So if you substitute instead of gamma r theta over L, so then we can, so gamma r theta over L, so we'll see how to get a relationship, and the torque T can be defined as r tau into dA. So that is tau into dA is the force in a small section, and if you integrate over the radius of it, then you will get the torque T. So then r tau into dA, and the integration over the radius can derive us a relationship as torque is equal to r tau into A. So the A is the area of the thin wall, that is 2 pi RT. Okay, 2 pi RT. So area of the thin wall. So now we have a relationship between T, that is r tau and A, and we know the A is 2 pi RT, and we also know that tau is equal to G gamma. Now gamma is equal to r theta over L, which we have obtained earlier. Then we have obtained this one recently. So tau is equal to T over Ra. So that is shear stress is equal to torque over R into A. And on the other hand, if we can get the theta is equal to L gamma over R. So gamma is the strain and R is the radius and L is the length. So if I substitute gamma is equal to tau over G, so tau over G, so gamma is equal to tau over G, then the tau is T over R into AG, and then means gamma is T over R into AG. So if I substitute that, theta is equal to LT over R squared AG. So this is another relationship. Now let us see how we can apply this in a real scenario. So a thin walled hollow circular cylinder has a mean diameter of 100 millimeter and a thickness of 2 millimeter and a length of 500 millimeter. So it's a cylinder, cylinder which is 500 millimeter long, and the diameter is 100 millimeter and the thickness is 2 millimeter. Now the first part of the question is, when this cylinder is subjected to an axial compressive load of 100 kilonewton, so axial load of 100 kilonewton, its length is shortened by 0.34 millimeter. So when you apply a axial load, the length is shortened by 0.3 millimeter. So that is delta is 0.34 millimeter. So strain is stress over strain. So strain is delta over L. So that is delta over L, that is delta A, and then this is stress is F over A. So F is 100 kilonewton. Area also known because we know the thickness and the diameter. So FL over sigma and A is 2 pi RT. So if you substitute in this equation, you will get the pressure or the stress. And then using the strain, we can determine the Young's modulus of the material. So Young's modulus is 234 gigapascal for axial force and axial stress. Then a torque of 800 Newton meter. So the torque of 800 Newton meter causes a twist of 0.16 degrees. So the theta is 0.16 degrees between the two ends of the cylinder. So now we need to find the shear modulus G. So G is shear stress over shear strain. Okay, shear stress over shear strain. So now we know the equations to find shear stress, and we know the equation to find shear strain, or we can use this equation as well. So 0.16 degrees can be converted into radians. That is very easy. And the shear strain is R theta over L, and shear stress is T over RA. So T over RA is T over R into 2 pi RT. And if you substitute this in this equation, so G is equal to 2 over gamma, and that is T over 2 pi R squared T into R theta over L. So then it becomes 2 pi R cube T theta O, and L comes on top. So this is derived from, say, G is equal to T over R into 2 pi RT into this gamma is R theta over L. So then L comes on the top, then the TL over 2 pi R cube to T theta. Okay, so now here we know that T is known, L is known, and R is known, and T is known, theta is known. So when you substitute all these, you get a value for shear modulus as 91.3 gigapascal. So this is the shear modulus, and then previously we found Young's modulus. Now let us look at a torsion of a solid circular shaft. So earlier we looked at thin wall. When it's a solid circular shaft, the assumptions we make are cross sections are circular and uniform along the shaft. The cross section doesn't change along the length. Material is linear elastic, isotropic, and homogeneous. And plane cross section before deformation remains plane after deformation. That means it is elastic, because it will go back to its original deformation. Straight radial lines before deformation remain straight radial lines after deformation. That is also mean elastic. So if you look at this, it's a solid shaft, length L, R radius, torque applied, resulting rotation theta. So if you derive an equation, so this is the relationship between strain and stress. So G R theta over L, this is strain. So G theta over L into R, this is derived from what we have done earlier. And for the torque is integration of the stress times area on this small area dA. And then if you look at that, it is R into F. So F is this, so tau into dA is F, so R into F is a torque. So that is integration of r into f. So if you substitute here r, and if you substitute tau g theta over L into r and dA, so you get g theta over L and the r square into dA. So r square into dA is, what is r square into dA? You might remember this is similar to second moment of area, but when it comes to a torque, it is called polar second moment of area, that is r square into dA, that is defined by J. So now we can substitute here J, so that becomes g theta over L into J. Okay, so you can refer about this polar second moment of area from previous studies, previous learning in the second year or in the first year. And for a circular area of radius r, the r square dA, the J is equal to r square dA, and then if you substitute dA is 2 pi r into dr, then that becomes 2 pi r to the 4 over 4. So that pi r to the 4 over 2 is the value of J for circular area. So if you substitute J here, g theta J over L, and g theta, then if you rearrange it, it's g theta over L in theta. So this is a constant, this is theta rotation, this is torque, so that is called torsional stiffness, gj over L. So using that we can determine the values. So if you look at this gj over L, you have then if you consider the shear strain, this is r theta over L, then you can substitute instead of theta in terms of torque, and for shear stress instead of G, you can find out you can substitute and find T over J into R. Okay, so here strain is T into G over J into R. Okay, so G is equal to G, or G gamma is equal to T over J into R if you rearrange this, and that is stress. So you have two equations. One is torque is equal to torsional stiffness into theta, and then the shear stress is equal to T over J into R. So if you correlate everything, if you relate everything, you get T over J is equal to tau over, so T over J is equal to tau over R, that is equal to G theta over L. So T over J from this equation is G theta over L. T over J from this equation is tau over R. So this is similar to sigma over Y, that is equal to M over I E over R. This is for beams, this is for shafts under torsion. Okay, so this is similar. Let us look at an example. Calculate the maximum torque that can be transmitted by a 100 mm diameter solid circular shaft if the working stress in shear is not exceed 30 Newton millimeter squared, and the angle of twist not to exceed 0.3 degrees per meter length of the shaft. So we need to find the maximum torque. So T max, and the diameter is 100 millimeter and solid circle. Working stress should be less than or equal to 30 Newton per millimeter squared. The angle of twist theta over L. should not exceed less than or equal to 0.3 degrees. Okay, theta L. So R is 50 because D is 100. Tau max is T over J into R. Okay, so T over J into R. So the stress varies from it's 0 closer to the radius, and it increases to the maximum when R is max. Okay, so when R max, then when R is equal to 50, you'll get the maximum tau max. Tau max, that is T over J into R, T, and then if you substitute J is equal to pi R for 2, then you get this equation. So here allowable stress is 30, so tau max should be less than or equal to tau allowable. So if you substitute in this equation, you get T should be less than or equal to tau allowable into pi R to the power cube. So R known, tau allowable is known, so you can substitute the values and get a torque value of 5.89 kilonewton meter. The limit angle. So theta over L allowable is 0.3. So that's why I marked as theta over L less than or equal to 0.3. So if it is 0.3, theta over L can be defined as T over Gj. So theta over L should be theta over L allowable, and then T over Gj should be less than or equal to 0.3. So T is less than or equal to Gj into 0.3. So 0.3 should be converted to radians. So then you will find this torque to be should be less than 4.32. So if it has to satisfy this condition, not exceeding the 0.3 degrees, it should be 4.32 kilonewton meter. If it has to satisfy working stress, it can go up to 5.89. So the lowest of these two will be the allowable torque, allowable maximum torque. Okay. Now if you look at a non-thin wall, how to look at the non-thin wall of a hollow circular shaft, then your integration goes from R1 to R naught, or Ri to R out, internal radius to out external radius. So simply your J value will be varying, the same equation is applicable, so you can use that using this same equation in a similar way, but only difference is your polar second moment of area is going to be different. Okay, that is for non-thin shafts. That means non-thin means R over T greater than, not greater than 10, it's R over T less than 10, then it is, this is thickness T and the radius R, and if it is hollow, it's called non-thin. Now let us see how we can use the torque to transmit power. So you can relate torque and the angular speed with power using this equation. You might have studied this in advanced level. So power is equal to torque into angular speed. So the omega angular speed is given in rotation per minute or revolutions per minute, and we need to convert that to radians per second. So this one also you might have done. So 1 RPM is 1 revolution per minute, so that is 2 pi over 60 radians per second. So now let us see an example. A solid circular shaft having a uniform diameter 400 mm connects a turbine to a generator in a hydropower station. If this shaft transmits 60 megawatt of power at a speed of 30 rpm, the torque in the shaft. So we know the power, we know the omega, so we can find the torque. So the diameter is 400, power is 60 megawatt, and shear modulus 80, R 200. So omega is 3000 into 2 pi over 60, that is in radians. 100 pi radians per second is the omega, that is revolutions per minute. If I substitute in this equation T is equal to P over omega, then you will get 190 kilonewton meter as the torque that is required to transfer this 60 megawatt power. Now the second question, twist per unit length of the shaft. So twist per unit length, so theta over L. So theta over L is T over Gj, and we know the T. If you substitute shear modulus and then polar second moment of area, then you will get the value twist per unit length as 9.45 into 10 to the minus 4 radian per meter. And the largest shear stress in the cross section of the shaft. The largest shear stress, the torque max, occurs when the radius is maximum, R max. R max is 200 millimeter. So if I substitute in this equation 2 into 2t over pi r cube, so 2t I know 190, and I know the radius as 0.2 meter, then it is 15.1 megapascal is what the torque max. So in this session we have discussed how to determine torque in a thin wall shaft and a solid shaft and a non-thin wall shaft. We also looked at how to calculate power transmitted using torque and the relationship between the power and the torque. Some of these you might have learned in advanced level, so it's easy for you to follow up. Other things that you can refer textbook and do more problem and familiarize yourself. So this session now ends for torsion, and we'll have another session in the next week. Please note that next week on Tuesday afternoon, mechanical students will have a separate session with Dr. Somaran, and civil students, Professor Niranga will take a session on materials related to highways. I need some more time to complete some other missing lectures. I will be in touch with the batch rep. Thank you.